Okay, hello everyone. Today we are very happy to have Professor Ofer Aharony from IS, and who probably does not need introduction for this audience. And today he will tell us about two-dimensional QCD as a string theory.
So thanks for the invitation. It's always great to be back here in Chicago. So today I'll talk about work that's still very much in progress in collaboration with my postdoc, Simon Kundu, and two my students, Tal Scheffer and Liv Jung. And the first results on one of the projects I'll describe appeared last month, but there's still many more results to come. So I'll begin with some motivations for why we should go back to this problem of describing two-dimensional QCD as a string theory. Well, it's been discussed, and some people think it's even been solved 30 years ago. And then I'll describe two different approaches to try to relate two-dimensional QCD to a string theory, one where we start from perturbation theory, and my main focus there will be on the example of two-dimensional massive adjoint QCD, and the other one where we start from string theory, and I'll focus on the case of pure two-dimensional young nulls. So the motivations. So almost exactly 50 years ago, Tuft first suggested this relation between large N gauge theories and string theory. So Tuft argued that if we take large N SUN gauge theories and consider them at the limit that n goes to infinity with a fixed we now call that the Tuft coupling, GN squared n, or if we will say fixed QCD scale, then they should be equivalent to string theories where the string coupling scales as 1/n. Now, the original arguments of Tuft were mostly based on just reorganizing the perturbation theory and gauge theory in the form of Riemann surfaces by the double line notation, and he showed that on the gauge theory side, you can map some finite diagrams to surfaces of genus G, such that the contribution of surfaces of genus G was like n to the power 2 minus 2g times some function of this adjoint coupling, and that's of course consistent with what we expect to get from a string theory with a string coupling which scales as 1/n. However, these arguments were not constructive, and they don't tell us how to construct a specific string theory that's dual to any given large N gauge theory. And for many years, there are almost no examples of this type of duality. Now, this changed significantly with the ADS CFT correspondence, which gave us many examples of concrete dualities of this type between specific large N gauge theories and specific string theories, which turned out to be just standard critical string theories, but living in rather complicated backgrounds with some extra dimensions compared to the gauge theory, and also with extra Ramon fields. But they are standard critical string theories. So we now do have many examples of this relation, but we still don't have any systematic way, given some large N gauge theory that we're interested in, for instance, QCD itself. We don't have any systematic way to find what is the string theory that's dual to it. So that's still an open problem. Now, one general direction to try to solve this problem is to first start from the limit of free gauge theories. So in principle, in free gauge theories, also there is still in free large N gauge theories, there is still a perturbative expansion in 1/n, and we try to start from the case of free gauge theories, which I think of as just the limit when this coupling goes to 0, and try to find their string dual, and then hopefully systematically add the gauge interactions on top of that. So of course, for free gauge theories, the dual string theory should be not a standard string, but it should be in some sense a tensile string. I mean, in free gauge theories, we just create states by saying things like trace of say raised to some power, which should be described by some collections of gluons that are just connected by some tensile strings or something like that. But there should still be a string dual even for free gauge theory, even though in that case it would be a non-standard string theory. And then that should perhaps be a useful starting point for them moving on to the interacting theory. However, even finding the string duals for free gauge theories turns out to be rather complicated, even though, of course, we know how to compute everything on the gauge theory side. And on the string theory side, it has turned out to be difficult to construct the duals even for those theories, and even for simple cases like the n equals 4 supreme Mills theory in 4 dimensions, where we do understand its string dual to some extent, and even in those cases, there's no good construction yet of the free limit of that theory. So in this talk, I'll go in a different direction and try to describe attempts to figure out this transition from gauge theories to string theory in the special case of two-dimensional gauge theories. So in this talk, I'll focus just on two-dimensional gauge theories, and we'll try to understand how to build their string dual. And so please just stop me with questions at any time. So two-dimensional gauge theories have two big advantages compared to their higher dimensional counterparts, which may make them easier examples with which to understand this gauge string duality. So one big advantage is that in two dimensions, the Coulomb force between charges already gives a linear potential. So this is true both in abelian gauge theories and in non-abelian gauge theories. So in two-dimensional gauge theories, if you want, confinement is seen already classically. So already classically, we put in two charges in a non-abelian gauge theory. They're connected by a string or by a flux line which behaves like a string whose tension is 1/2 g mole squared times n. And that means that in these theories, sort of standard string theories in which the string does have a finite tension, and we see and standard behavior can arise already just classically in perturbation theory. So already in perturbation theory, we do see that we have linear forces between charges. So one can hope that already in perturbation theory, we should be able to reproduce many properties that we expect from a dual string theory. And that's what I'll describe in the second part of the talk. Starting from perturbation theory, we can finally see strings emerge, and hopefully in a constructive way that will allow us to eventually construct the dual string theory. So that's one advantage of two dimensions. Another advantage of two dimensions is that in two dimensions, we don't have any dynamical gluons. So dimensions, the gluon field has d-2 physical components or physical polarizations. And in two dimensions, the gluon has no physical polarizations. And in particular, if we look at the pure two-dimensional Yang-Mills theory, then that theory actually has no physical states, since there are no dynamical gluons. So it is still a confining theory in the sense that if you put in Russell lines, there is a linear potential between them, but it does not have any physical states. And in fact, the pure two-dimensional Yang-Mills theory, as I'll remind you in the third part of the talk, is exactly solvable. And moreover, its solution can be recast in the larger limit as a string theory. And this was in principle done already by Russ and Taylor more than 3 years ago. So in this case, the dual string theory has the special property that the string is not allowed to fold. So in two dimensions, so two dimensions here means 1 + 1 dimension. So we just have one spatial dimension. So in order to get any physical state, then the string has to fold back on itself and create a state like that. But the specific strings that are dual to the pure two-dimensional Yang-Mills theory have the property that they're not allowed to fold. And that in some sense explains why they do not have any physical states. So assuming that now I'll describe the status of finding a worldsheet description of this string theory in the third part of my talk. But assuming that we can find a worldsheet description for this string theory dual for the pure two-dimensional Yang-Mills theory, then in principle we can then just add to it matter fields. For instance, if we have a string dual to the pure 2D Yang-Mills theory, then if we just add to it dynamical boundaries with massive particles, then that should correspond in the field theory to adding fields in the fundamental representation. So that should give us, if we take these fields to be fermions, then that should give us the 't Hooft model. We also take them to be scalars, and we get scalar versions of the 't Hooft model. So in principle, once we understand the string theory dual of pure 2D Yang-Mills, then there's well-defined way to go from there to a string theory dual for the 't Hooft model, which is not yet known. And then we can also try to add to that particles in the adjoint representation. So particles in the adjoint representation are described by extra particles on the worldsheet where the string is allowed to fold. So they would be described by configurations like this. But at least if we take these particles to be very massive, so if their mass is much larger than, say, the scale set by the gauge coupling in a two-dimensional gauge theory, then one might expect these particles to be weakly coupled. So again, there should be it should be possible to construct a string theory for adjoint QCD in two dimensions by just starting from the string dual of the in principle non-string dual of the pure two-dimensional Young-Mills theory, and then adding some particles on the worldsheet on top of that. So the hope is that there is a systematic way to construct the string duals of all 2D Young-Mills series just by starting from the pure Young-Mills case and then just adding boundaries or extra particles on top of that. And we'll describe what we know about that so far in the third part of this talk. So that's the motivation, and then the rest of this talk I'll describe how far we managed to go in each of these two directions so far. So
So the tooth model, I guess, is solvable from the field theory side. Like, are the
Young-Mills theory, that's the tooth model, yeah, it's all at large end, it's solvable from the field theory side, right? But it's just not that when reproduced from a string theory.
okay? So you want to find a string theory that will
There should be a string theory whose spectrum at large n exactly reproduces the Tooth equation and gives exactly the spectrum of that Tooth model, and that's not yet known. Okay. But in principle, if we have this, the string dual of the 2D Young-Mills theory, then it's just a question of finding the right boundary conditions and quantizing them, and that should give that Tooth model. Right. So once that string theory is understood, it becomes just a technical question in some sense. And of course, the same is true also in higher dimensions. I mean, if we can find the string dual of pure four-dimensional Young-Mills theory, then again, if we just add the dynamical boundaries, that would give us also the case of dynamical force there and so on. So the hard part is mostly understanding the string dual of the pure Young-Mills theory. Any additional questions? Okay, so let's start with the second part, where we'll use perturbation theory to analyze two-dimensional massive adjoint QCD. So the theory that we want to describe in this part is massive adjoint QCD. So the action is just a kinetic term. So we'll discuss SUN or UN gauge theories. So the action, that's the gauge kinetic term. It has one fermion and the adjoint representation coupled with the gauge field, and it can be massive. And we expect again that if this mass is large compared to the scale set by the Young-Mills coupling, then maybe the theory should be coupled, since in two dimensions gauge interactions become weaker at high energies. So this is the action that we're going to start from. And again, the question is, can we go from this action to some picture like the picture I described, where we think of these fermions as excitations along some string that allow it to fold in this way. So this action was analyzed in detail by many people, and in particular, I'll follow the presentation by Gustav from around 30 years ago. So this action, so of course, in general, it's some interacting theory, but again, you can do perturbation theory and coupling at high energies or when the mass is large. And one way to simplify the analysis of this action is to go to light-cone gauge, as I took it in the analysis of the Tooth model, also more or less 50 years ago. So we'll define the light-cone coordinates, sigma plus minus, the usual way, plus or minus sigma 1, and light-cone gauge is just the gauge where we set one of the light-cone components of the gauge field A minus to 0. And that, of course, gets rid of all the Young-Mills interactions. I mean, so the only interaction that remains is an interaction here in the square derivative between A plus and the fermions. Now the fermion field is a two-component spinner, and we can choose some convenient basis. The gamma matrix is generated in this way, and then once we do that, then the action gets the following form. And so out of the gauge kinetic term, all that's left is B minus B plus squared in this gauge. The fermions, when we go to these light-cone coordinates, it turns out that one of them has a kinetic term that's purely left over. I mean, so gamma plus here is not there. Only it has just a non-zero element here, and gamma minus has a non-zero element on the bottom right. So one of the fermions is purely left moving, the other one is purely right moving, but there's a zero. Of course, it's a massive fermion, which is neither purely left moving nor right moving. So we have this mass term that relates them. And then the only interaction term is an interaction term that couples A plus to a current, where this current is of the fermion by Venner. I mean, so it's in this gauge, it's just the same as the product of tube size. So this is the precise form of the action in this gauge. And then in order to further simplify the analysis, we can note that two of the fields have kinetic terms with only d minus derivatives, and one of them has kinetic terms that only has d plus derivatives. So we can simplify things even further by doing a light cone quantization of this theory. So I'll choose sigma plus to be the light cone time direction, which will evolve in, and sigma minus will be a spatial direction. And then both chi and this A plus field don't have any time derivatives in their action, so they can be viewed as auxiliary fields, which can be integrated out. And so after integrating them out, we're left with a theory that has a single dynamical field, which is just the fermion and adjoint representation, this psi, and the branch that we get describing for the psi is just time psi plus psi, which is just copied from here. Then from integrating out the gauge field, we get an interaction between two G classes, but a non-local interaction between them because we have the reverse powers of this light cone spatial derivative. So we have J plus times 1 over d minus squared J plus. And then from integrating out this extra fermion chi, we get an extra mass term. So the mass term in the light cone frame looks like m squared divided by the light cone momentum. So it looks like m squared over d minus is what we expect. So this is the expression that we get for the Lagrangian in this light cone frame. And then on top of that, there's also still a Gauss law constraint that I'm not writing down, which still remains as one of the equations of motion of A plus. So we get this interaction, which is now more complicated because it has these non-local interactions between the psi's, but on the other hand, we just have one field. And this non-local interaction looks complicated, but in momentum space, it can be simplified. So we can go to momentum space, and so we have first momentum modes psi AB of k. So these denotes the AB component of this adjoint matrix with some momentum k in the spatial light cone direction, and they obey just from canonical quantization of this action, then they obey the following anti-commutation relations. So that we can choose a vacuum, which is so that if we ignore the interaction and we just look at the kinetic term, then the vacuum is then the operators of k with k, the operators of psi with k positive raise the energy. I mean, they have a positive energy here, m squared over k, and so the vacuum is annihilated by all these psi BKs with k bigger than 0, and then we can discuss general states here by just acting on this vacuum with these creation operators that have positive light cone momentum, and we need to find states that should be singlets of SUN. I mean, that's what we get from this Gauss law constraint, and that will diagonalize the Hamiltonian. So instead of working in the Lagrangian formalism, we can work in the Hamiltonian formalism. So if we translate this Lagrangian into Hamiltonian, then the kinetic term in momentum space, and it just looks like an integral dk over k of. So your normal ordering things, so that we only have sort of the psi's with positive momentum are to the left of the ones with negative momentum. So in the Hamiltonian, we have this mass term, which is just the standard light cone mass term, and we have this interaction term, which is a bit more complicated. So that has k over k squared. This current plus with 1 to minus k to k. I'll write it in terms of fermions in a moment in a more explicit way. So we have the light cone Hamiltonian, we have the spatial momentum in the light cone frame, which is obviously just the k of psi minus k psi k. And as usual in the light cone frame, we have the relation that the mass squared of any state is given by the normalization of 2 times the Hamiltonian times this light cone momentum. So all the states have a positive light cone. So we're using these light cone time coordinates. So this is the sigma plus coordinate and this is the sigma minus coordinate. These are the usual time and space coordinates. So we're evolving forward in this light cone time, and all the states have positive light cone momentum given by basically counting these excitations of the fermions, and we need to diagonalize the Hamiltonian in this Hilbert space. So that's the essential problem of adjoint QCD. And to be more explicit, we can write out this interaction more explicitly. So each of these states is some fermion by linear. So if you write down the interaction more explicitly, it takes this form. So the Hamiltonian, again, we have this kinetic term, which is the free kinetic term, and the light cone frame. I mean, the only slight subtleties when we normal order this four-form interaction, then it also gives rise to another quadratic term. So that's why there's this shift in the mass here coming from the normal ordering. So that's this shift in the kinetic term. And then on top of that, we have four-form interactions. And there are several different types of interactions. So there are these interactions which take 2 particles to 2 particles, and so essentially you can think of those as having these 2 fermions, which are originally exchanging gluon, but once we integrate it out the gluon, then this just becomes sort of a non-local 4-Fermi interaction of this form that has this form in momentum space. And in particular, this 1/k1 minus k4 squared is exactly what comes from integrating out the gluons that give rise to the Coulomb force. So this is this term is just the Coulomb potential written in this language of the light cone frame. So you'll recognize the Fourier transform of 1/k squared in one spatial dimension is sort of absolute value of sigma minus, which is the Coulomb potential. And on top of that, there are these 2-to-2 interactions which are given by this formula. But then there are also these other interactions which can take either 1 fermion to 3 fermions or 3 fermions to 1 fermion, and you get this explicit form. So we have both particle number conserving interactions and particle number changing interactions, which take this form. And what we need to do is to diagonalize this Hamiltonian. So that's the setup that we want to work in. And so for instance, unfortunately, because we have these particle number changing interactions, we can't just work with a fixed particle number. We have to construct states that are made from any number of particles. But the number of particles is preserved modulo 2. So states that have an even number of psi's are bosonic states. States with an odd number of psi's are fermionic. So for instance, if we want to construct a generic bosonic glue ball state made out of, should probably call these Lorena balls or whatever, just states made out of these adjoint fermions. So a generic bosonic state made from these adjoint fermions would be a sum overall even particle numbers of some variance, or with each particle number, then the appropriate normalization. We have some wave function in this light cone momentum. So we have some wave function by n of these momenta, and we have okay, yeah. So if we want to say that whenever we have a particle, since we have a boost symmetry in this theory or part of the Lorentz symmetry, we can always choose any particle state that have momentum 1, say, just by boosting it to that frame. So we can look at, so when we diagonalize the Hamiltonian, we can diagonalize it just in the sector of states that have p equals 1, and then of course boost them to get the same state with any other momentum. So if you focus on p equals 1, then we're interested in constructing wave functions that are only non-zero when the sum of all z momenta is equal to 1. And when the states are given just by acting with these great fermionic operators on the vacuum. So this is in some sense the most general bosonic state in this theory. more precisely, this is the most generic state that's gauge invariant and that has just one trace. We could also construct similar states with more than one trace. But in the large limit, we expect that single particle states will be predominantly given by a single trace, and so there will be mixing over 1 over n with multi-trace states. So at leading order in the large limit, at least we can focus just on single trace states, and they take this form. So if we're just looking at single traces, then we just have one wave function for every n, and what we need to do is plug this into the Hamiltonian and try to diagonalize it. So these functions phi n are a priori defined for any case between 0 and 1. They need to be cyclically invariant because this trace is obviously cyclically invariant. So they're cyclically invariant among their n arguments, and they always obey a boundary condition that if we take one of the momenta to 0, then the wave function vanishes. So this is sort of obvious because if we take one of the momenta to 0, then it costs us infinite energy because of this the format of the kinetic term. So in principle, this is a well-defined quantum mechanics problem now to find the spectrum of this adjoint QCD theory. But of course, in general, it's very complicated, and even in the limit of large mass, then this is a rather complicated problem because of this mixing between the sectors of different particle numbers. However, well, what we'd like to do, at least for a start, is to analyze this problem at high energies. So we're going to look at energies that are much Lycon energies that are much larger than the mass, and we also want to be coupled, so the mass to be much larger than J equals squared n. So here we're looking at the very high energy spectrum. So this is analogous in the network model. Also, if you look at the very high energy limit, then it's easy to write down the precise states at high energies. And we're going to do the analogous thing here. So one may hope that if we go to very high energies, then the dominant contribution from the Hamiltonian will come from this Coulomb potential term, because this is the only term that can actually diverge. I mean, if all the other denominators here never become 0, but here the denominator can become 0 when these two k's become equal, so that corresponds to the long range Coulomb force. And one may hope that term could dominate the long range, the interactions in the high energy states. So what we'll do is we'll write the Hamiltonian version is some. Yes, please.
Do you need to impose another condition when two momenta become close to each other? I mean, I guess it goes to 0, but does it go to 0 because of fermionic?
No, if two momenta, yeah.
But does it go to
it goes to 0 if they're exactly equal? But yeah, but
does it go to 0 fast enough?
That's sort of automatic from here,
But does it go to 0 fast enough?
Only if it's two momenta that are adjacent in this trace. If they're not adjacent, then it doesn't even go to 0. So.
Great. Yeah. So should you impose something, because it looks like you're
even you don't need to impose something, but it may cost you a lot of energies. I mean, so yeah, so when you expect that the high energy states will not include momenta coming close together because of that. But I mean, it's not something we need to impose by hand. I mean, it's something that should automatically come up.
Right. I mean, you imposed by hand that 0 momentum, the wave function has to vanish to suppress.
Yeah, so just to solve it as a boundary condition for solving whatever differential equation that we get when we get this. But yeah, but we don't need to impose anything extra when the momentum become equal.
And what phenomenon happens when we tune m squared through g squared n?
Yeah, so I think that's exactly the point where it becomes supersymmetric. I'm not sure. Yeah, here on they talk about the large mass limit. So yeah, I don't remember exactly, but I think that maybe the point where the small becomes supersymmetric. So there's a special value where the small becomes supersymmetric, even though it's not obvious. And I think it might be exactly at this value, and then.
But there's no pathology when you go to the other side.
Yeah, so you think that this becomes negative, but the interactions do overcome for that. I mean, there's a pathology if f squared becomes too small, of course, but yeah, but as long as it's positive, I think there's no pathology even when you go below that value. But yeah, but that's not the regime we want to be in. We want to be in the opposite regime. But I think the model is fine also there.
I mean, as long as the mass square is positive.
Right, as long as it's positive.
Not the coefficient there.
Yes, but not, yeah, coefficient is before math, it's still become negative. So yeah. that's true that the interactions always give enough energy to preserve the unitarity of it, even when that becomes negative. Any other questions? So the approximation we'll use to analyze this theory is to, the first approximation, keep only the Coulomb interaction, so only this this term in the Hamiltonian. So if we just keep that term in the Hamiltonian, well, we keep that term in the Hamiltonian, and in fact, well, simplify it even further. So we'll approximate the Hamiltonian. So first of all, of course, if we keep just the Coulomb term, then we don't have these interactions that makes different particle numbers, so we can solve it particle number by particle number. And then form of the Hamiltonian, just recount the following. So square root of 2 pi. Sorry. So the squared with shifted. Of this. So, well, in the original Hamiltonian, we also had an integral here that just goes between 0 and 1, but we can approximate, since we believe that the main contribution to the energy will come from the regime where this is close to 0, then we can approximate it by expanding the range of the interaction from -infinity to infinity, at least formally. So this is the what we'll call H0, and then H1 is just H minus this H0. And it turns out that this Hamiltonian is actually easy to solve. So here we just have this 1 over k squared interaction, but if we do a Fourier transform back to position space, so we consider the wave functions in position space instead of in momentum space. So I'll denote the position space by x, which is a sigma minus. So if you translate this back to position space, then the Fourier transform of this 1 over k squared, as we say, is just the absolute value of sigma. So what we find in position space is that the Hamiltonian is just the sum of the distances between the positions of the different adjoint particles. So the picture should be that we have these adjoint particles located at these different positions, and the interaction just comes from the sum of the energies of these strings stretched between them. So in that sense, this is sort of automatically stringy type Hamiltonian, as we may have expected. At first sight, it may sound very surprising that our Hamiltonian will be diagonal in position space, because of course you may expect that if you have two particles connected by string, then of course the string pulls them together. So we would expect that if you start from these two particles connected by string, I mean, there's a string will shrink and then expand back again, and then shrink again, and so on. So there should be some time evolution like this, as is also familiar from the Hooft model. And indeed, this is the correct picture for what happens in the usual space. However, if you look at the same picture in this light cone time coordinate, then in the light cone time coordinate, then the distances between the positions of the two particles along the string always stay fixed throughout this light cone time evolution. They just exchange positions, but the distance between them stays the same. So for the two particle state, then this would just give us G1 squared n times the distance between them, and in this approximation, we're in this ultra-relativistic approximation, so the particles really just cross each other instantaneously, and we have a time evolution like this, where the distances remain fixed, and you can show that the same remains true also when you look at n particle state. So all these particles, each particle eventually gets reflected at the end of the string and so on, but all these things happen instantaneously in this light cone frame, so that this position space basis really does diagonalize the Hamiltonian.
What happens at these instantaneous jumps?
Yes.
What term of the Hamiltonian implements these jumps where particles magically jump across each other?
So they're not really implemented by that. They're sort of implemented by the boundary condition we choose for this for these phi n's. I mean, so the boundary conditions. So in momentum space, of course, the wave functions of these are the sums of exponentials, which I'll write in a moment. And the boundary condition that tells us that you have to reflect is that it tells us that you have to take some specific combination of these exponentials, which will, like in that Hooft model, you just have sines and not cosines, say, of the wave functions or sines of to model the wave function would be something like sine of n sigma or something, and not so this would be a specific combination that obeys the boundary conditions, and then that implements the fact that the string has to go in some sense back and forth instantaneously. I mean, so of course, if we wouldn't put in boundary conditions, then you could just have plane waves that it was just where these positions will just continue going forever. But in some sense, putting these boundary conditions is what implements that. I mean, that gives us finite energy states which do have this. But yeah, I mean, it's not. Maybe there's more to be said than that. I'm not sure, but anyway, the wave functions that we constructed do have this behavior. So I can just write down what the wave functions are. So our claim is that a full basis of eigenstates of this Hamiltonian. So some of these eigenstates were found already by David 30 years ago, and some additional ones were found in a recent paper by Uwe Trittmann. But we claim that we have all the eigenstates of this Hamiltonian in this approximation. So in this approximation, the eigenstates of a Hamiltonian are given by n integers Li corresponding to the different segments of this string. And they need to satisfy that their sum is 0, and we can always, in order to specify a unique wave function, we can always choose them to be in monotonic order. So a generic state of the string is in this limit. It's characterized by these n integers summing to 0, and then we can always shift the state so that one of the positions is at 0, and then the next particle is at L1, the second particle is at L2, and so on. So you can always choose it to be at 0, and then you can explicitly write down the wave function. And the explicit wave function is the sum over all permutations of these n particles, where each permutation is weighed by the sign of the permutations times just an exponent of by times the momentum ki times these x's, but of the permuted set of L's. So we have these numbers. We have them with all possible permutations corresponding in some sense to all the different ordering of these different segments along the strings, and then the state takes this form. So, of course, if we just have a two-particle state, then this becomes e to the 2 pi I kx minus e to the minus 2 pi kx. So that's just this sign which describes these two particles exchanging places. And the sum over all these permutations with these signs correspond to really all the possible ways for these particles to be reflected back correctly. So this correctly takes into account all the boundary conditions, and it is also an eigenstate of the Hamiltonian in this approximation. And,
what is the approximation so far?
So the approximation is just keeping only this single term of the Hamiltonian, and even in that term, the interval to go from minus infinity to infinity instead of from 0 to infinity. So it's a severe approximation, but when we hope that it's true at very high energies, I'll describe in a moment to what extent it's true. But in that approximation, we can't solve exactly for the spectrum, and the spectrum is, so this is the full spectrum of the 30, and the energies of these states are just given by g squared n times the sum of these absolute values of these lengths. That's what we expect from this position space picture. So in this approximation, this is the full spectrum, and we do have this very simple stringy picture. So these are the sort of non-interacting particles just contained by these sort of rigid rods in this approximation. And this is, and again, this is the complete set of eigenstates in this limit. And it's easy to compute the density of these states. So if you want to ask how many states do you have at a given energy, then we sort of just have
M
to.
squared drops out from the eigenstate.
Yeah, in this limit, yes. In this limit, we didn't even keep the mass term. I mean, so this 8,0 didn't include the mass term. So in this limit, it completely drops out. I mean, as you may expect for very high energies, I mean, these particles are always going to be almost relativistic, and the mass is negligible.
And can you check that particle number changing processes are indeed suppressed for these wave functions?
I'll answer that in 1 minute. So yeah, so of course there are going to be corrections to this, both from the mass terms and from particle changing processes and so on, which I'll describe in a moment. But before I say that, let's just say what's the density of states that we find in this approximation. So in this approximation, to find the density of states, so again, this is the density of states in the Lagrange Hamiltonian, but it's easy to map that to the mass using the formulas that I gave. And in the light Hamiltonian, if we have a state with some number n, and we just have to count the number of partitions of that to positive and negative integers in this way. And so it's easy to compute the density of states, and we find that the density of states at large mass has a high-norm behavior, as one may expect from such a string theory, with the following precise coefficients. So it's given by the string tension times some specific number that we can find from this analysis. So this is a solution to 2D adjoint QCD in this approximation where we only keep the mass term in this Coulomb potential. And the question is this a good approximation or not? So indeed, in the truth model, this is a good approximation at very high energies, because there you can indeed neglect the masses and show that the corrections to this are small. But in adjoint QCD, the problem is that we do have also these particle changing interactions. And even though these particle changing interactions, so originally we thought that these particle changing interactions would all be negligible because they don't have this growth like the Coulomb potential term does. And so originally we were hoping that they would be negligible at high energies and that this would really be the exact high energy behavior. But unfortunately, it seems not to be the case that they're completely negligible. And essentially the reason for that is that even though the specific matrix elements that connect, say, an n particle state to an n+2 particle state are not large, unlike this Coulomb potential term that does become large, then there is a large phase space associated with the creation of these extra particles, which can be sort of created anywhere along the string, and that does give rise to corrections which are not negligible. So what we're still working on is understanding precisely the nature of these corrections. So we do seem to find that these corrections are small, so otherwise I wouldn't be telling you about this leading approximation. I mean, so it does seem that this is a good approximation in the sense that the corrections are small, but they're not parametrically small. I mean, it seems that even at arbitrarily high energies, they're around 10% corrections, which to some extent we can analyze analytically by just focusing on sort of the leading terms that contribute at high energies, but we don't have precise results from them yet. So that's still a work in progress, but our hope is that we will be able to show that these corrections are indeed small, and therefore this approximation that we started from is a good approximation to find the spectrum and also the high-order density of states and so on. But of course, to claim that, we do still need to understand better the corrections, and that's still not completely clear. Sorry, just one more sentence and then I finish this part and then the question. So that is still a work in progress. But sort of independently of that, it's clear that we can try to construct a string worldsheet theory that would just reproduce directly this Hamiltonian that we find from the field theory. So in this leading approximation, we just find this rigid string connecting these particles, but we know that the exact Hamiltonian is given by this rigid Hamiltonian plus these very specific interactions between these sides, which you can think of again just as these particles moving along the worldsheet now with some fixed mass and with some very specific interactions between them. So in principle, it should be possible to take this Hamiltonian and just translate it into some Lightcone Hamiltonian of this string, and in that way systematically build what should be the string level of 2D massive adjoint QCD. But so far we have not been able to do that, but I'm still optimistic that it should be doable. So that's the end of this second part of this talk. And question.
Yes, I'm wondering if you can add a control parameter to make this controlled, or more specifically, if there's a sector of states that are kind of non-relativistic and that have no number.
Yeah, well, there are always states that are non-relativistic in the sense that you can always, if you're at a given energy level, you can always look at the states that H is approximately just the mass time, the mass squared times.
So the correction, does it get smaller?
Some of the masses and so on. So there are always non-relativistic states where most of the energy is given by the mass. But those states don't give the main contribution to the spectrum. I mean, the generic states don't look like that, but they look like these. The non-relativistic states can be solved exactly and so on. I mean, David also had some papers about that and others. So and the non-relativistic states where the energy is slightly smaller than the rest of us, those can certainly be analyzed.
So your 10% is some kind of average error. I guess it's
No,
small.
10% is in this high energy limit. So sorry, the 10% is still in this high energy limit. So we're hoping that if high energy limits, the correction will just go to zero, but it doesn't look like they go to zero, but it still looks like they're small numerically, at least they seem to be small, but again, we don't have any control parameter yet. So this 10% is an estimate for these energies much larger than the mass still. I mean, otherwise, definitely you could have much larger current, of course. If it's in the non-relativistic limit, of course, the energy is dominated by the mass, and this is just a tiny correction to that and so on. So yeah, of course, those behave very differently. But at high energies, one may expect simplifications. Again, when we started the project, we were hoping that it would simplify further because it's going to become a weakly coupled theory. I mean, it's really much better than asymptotically free theory. I mean, in the gauge theory, it is really weakly coupled at high energies, but it seems like still the interactions cannot be completely neglected. So we still need to work harder to understand.
Is there an assumption that each of these partons is individually carrying high momentum?
Yes, I think so.
So-
Well, okay, I'm not sure what you mean by high
Well-
momentum, but high energy. I mean, of course, the electron momentum is fixed to one. I mean, and
Yeah,
divided among these partons, but each one of them carry the high energy individually. Yes.
So, but if you admit these particle creation processes, you're sort of fractionating that
Yeah.
energy
that's
among
right.
its constituents. So do you have to worry about sort of getting out of the approximation that you're working in? Because the particle, the effect of it is creating
Yeah.
more and more pairs of
Yeah.
particles is to push you away from the high energy regime
Right.
per parton.
Yes. So I think not in the sense that I think that, I mean, the generic particles here would carry an energy that's, I mean, they sort of have an occupation number, which is maybe sort of the square root of the naive energy that you would get by just dividing it equally among all the masses of all the particles or something. So
It's like you're assuming that all of the partons are sort of like valence partons, and there are no weak partons.
yeah.
But
Right.
if I start creating partons, they can carry any amount of energy, including
yeah.
not so much
Yeah,
energy.
no, that's true, but I think the weak partons don't contribute significantly. Okay, we still need to check.
But
what
that's
more
why it's
carefully.
uncontrolled, right? I mean,
I mean, the weak. I mean, in terms of, I mean, again, the only thing that enhances the interactions is the fact that you have these sort of long strings, and then there's a phase space for these particles to be created anywhere along the strings. Well, the weak partons would be sort of things that are created, the edges and so on. So they're not so enhanced. I mean, so I think the dominant contribution does really come from when it's long, and if it's not long, then these things will just not be enhanced, so they would not contribute so much. So we think it can be controlled, but again, since we haven't done it completely systematically, I can't
Okay.
give better arguments than that. But we believe that it can be controlled, but we're not completely sure yet. But I do think that typical states will still behave like this. I mean, again, with a large number of partons, but not large enough that the approximation will break down. But again, that's just a belief based on work so far, so it's justified. Any further questions about the second part?
how did your error scale with the little n, the number of, is it?
How does what scale?
That's the error.
Yeah, it decreases. It decreases a bit. I mean, it looks like the largest error is like for the states that are dominantly two particle states, and then it decreases, but it doesn't go all the way down to zero. So yeah, so it does look like the two particle states, and so the two particle states are sort of two of these adjoints connected by two strings and oscillating and so on. And so those seem to mix like, so those seem to have sort of the largest mixing with higher particle states in some sense. And yeah, for the other ones, it's less, and maybe in some sense because these have the longest strings between them and so on. So there's a bigger phase space enhancement, and then the more particles you have, there's phase space enhancement is smaller, so the corrections are smaller, but it is still there for all. So I have about 20 minutes left, I guess. Yeah, okay, this should be enough for the third part. Okay, so third part is now to go to a completely different approach and try to build the string theory dual to 2D gauge theories by starting from the case of pure two-dimensional young nulls. And again, in principle, if we solve that, then we can systematically, just from the string theory point of view, also add matter fields and see what they do. So we're now discussing just very two-dimensional young nulls, and so the Lagrange is just the usual two-dimensional in most Lagrangian, and because we're in two dimensions, this has no dynamical degrees of freedom. Now, if we put this theory on a circle and try to compute the spectrum of the theory on a circle with some circumference L, then when we put the theory on a circle, there is a dynamical degree of freedom, which is the holonomy of the gauge field along that circle, and it's easy to quantize that theory exactly. And so the exact spectrum of the theory on the circle, you can find that there's one state corresponding to every representation of the gauge group, whose energy is exactly given by GML squared over 2 times the circumference of the circle times the second Casimir of the representation. So again, this is a even though it's a non-abelian gauge theory, then because it has no particle states, the Hamiltonian can be exactly diagonalized in this form. So there's one state per representation of the gauge group. And then, so this sort of gives us the spectral theory on a cylinder. And then by gluing together these cylinders, people were able to construct, again, already more than 30 years ago, the partition function for this 2D Knowles theory on a genus G Riemann surface. So we're gonna, if we put this Knowles theory on a genus G Riemann surface, then the partition function takes the following form. So, well, if we put it on a torus, then obviously we just evolve in time with these states, and we have a factor that looks like e to the minus diagonal squared over 2 times the area of the torus coming from this length times the length of the time direction times this second Casimir. So on a torus, then this would be the complete answer, and it turns out that on a manifold of other genera, then there's just one extra term, which is the dimension of the representation r raised to the power 2 minus 2g. So that's the exact solution for the partition function of the 2D Knowles theory within a gauge group that again was found many years ago. And I won't give all the citations for that, but it can be found that paper. So this 2D Knowles theory is exactly solvable, and the question is, can we find a dual string theory for it? So again, this here, of course, it's exactly solvable for any value of n, but to find a dual string theory, we'd like to take the larger limit of this with a fixed Hooke coupling and ask whether we can do a 1/n expansion of this that would look like a string theory. So we can look at the partition function. Also, it's possible to compute exactly also the Wilson line expectation values in this theory and so on. All of them have explicit expressions, and we can ask what they behave like in the larger limit, and do they behave like string theories. So what happens if we take n to infinity, again, keeping fixed GML squared times n? So the first question is which representations in this sum survive? So this was analyzed by Gross and Taylor a bit more than 30 years ago. And it's sort of obvious that the representations that will survive are the ones that have second Casimirs that are of order n rather than of any higher order n. And what they argued is that those representations are the representations that have a Young tableau that correspond to some representation with a number of boxes that remains finite in the large n limit, multiplied by a representation that's sort of the complement of some representation like that. So if this is n rows of the Young tableau, then there's some representation, then the representation that survive in this limit or the products of a representation R and the complement of a representation R bar. So if this complement has the same second Casimir as the original representation, so that also has a second Casimir that remains finite as n goes to infinity, but all other representations have Casimirs that grow faster so that they would not contribute in this larger limit. And then what Gross and Taylor showed is that this partition function can be rewritten in this limit as the sum over, well, first of all, it has a 1/n expansion in this limit. And what that 1/n expansion looks like. So we can identify terms that go like n to the power 2 minus 2g with the contribution of worldsheets of genus G in the string theory as usual. We have a sum over 2 integers and then tilde, which are essentially the number of boxes in this first Young tableau and this other Young tableau, which corresponds to the complemented representation. In this limit, well, the leading thing that survives out of this exponential term in the area is just the push times the area over 2. So these types of representations, leading order in the large n limit, their second Casimir is just n plus n tilde. If we have n boxes here and n tilde boxes here, then the leading order in n contribution to the Casimir is just n plus n tilde times big N. So that's what gives this contribution. And then this is multiplied by some over terms that are polynomial in the area. So it should come from expanding the other corrections to the Casimir in a 1/n expansion. So that gives rise to various extra power law terms in the area with some coefficients that I won't try to explicitly, which depend on the genus of the worldsheet, the genus of space-time, and on these points. So anyway, this is an exact rewriting of this expansion of this expression just in the large n limit. And it's natural to then interpret this expansion as a string theory that has so we interpret the contribution here from genus D is coming from a worldsheet of genus D, a string theory with string coupling goes like 1 over n in an obvious way, and with a string length, it's just lambda over 2 corresponding to this term. So the idea is that the contributions here that have some number n and tilde are interpreted as having the string worldsheet wrapping the space-time n times with one orientation and tilde times with the other orientation, such that altogether it winds around the space-time n plus n tilde times, and that's what gives this factor. And then these mappings from the worldsheet to space-time, they can have various special points in the mapping, various branch points, and so on. And then these extra terms come from counting how many mappings there are with I special points on them. That okay, I won't need all the details of this for here. I mean, these coefficients also depend on whether the gauge group is SUN or UN, because there's a somewhat different expansion in these two theories. But anyway, there are very specific numbers here that one can find. So that's what Gorse and Taylor did, and what they wrote indeed looks like a string theory, but they didn't give any worldsheet that reproduces this string theory. So the question is, can we find a worldsheet action that would reproduce this type of expansion? And we want to have a worldsheet theory in order to be able to continue with this program that I described. If we have a worldsheet, we can add some boundary conditions and get the truth model from these dynamical boundaries and so on. Well, of course, if we don't have a worldsheet, then it's not clear how to do that. So this question of constructing a worldsheet that will reproduce this Gross-Taylor expansion, again, has been around for more than 30 years. There are some sectors where it's relatively easy to do this. So if you look at worldsheets that only wind with, it's natural to interpret these terms with n and tilde as again having a worldsheet that winds around the space-time n times with one orientation and tilde times with the opposite orientation. But if you have terms that correspond to all the windings having the same orientation, so if n tilde is equal to 0, then it's easy to convince oneself that one can describe the theory as just containing holomorphic mappings from the worldsheet to the space-time. Of course, any holomorphic mapping always has all the windings of the same orientation. So this is what's called, sometimes called the chiral Yang-Mills theory. And that can be described as the sum of just holomorphic mappings from the space-time to the worldsheet. And of course, in string theory, we are familiar with many different ways of constructing string theories that count the number of holomorphic maps from a worldsheet to a spacetime. So various people, starting with towards Moore and Margulam, and then various others through the years, have suggested various ways of building string theories that will reproduce this chiral sector of the Yang-Mills theory that describes again the sector where we only look at mappings with one orientation. But of course, fortunately, we do want to look at the sector that has strings with both orientations. In particular, even if we just look at the Tuft model, then we expect states in the Tuft model to we have this quark and dynamic quark connected by string, but then we expect them to exchange places so that under the evolution we will have a string with one orientation that goes to a string with another orientation and so on. I mean, so obviously we do need to include strings with both orientations if we want to describe correctly the Tuft model or any other more complicated interacting theory. So this is not enough. And the question is, can one find a worldsheet that will reproduce the full non-chiral sum here? And for that, there's still relatively few results. So, I mean, there have been some attempts to do it. Now, the problem with including also both oriented and non-oriented mappings is that the mapping from the worldsheet to spacetime in that case necessarily has to be singular. For instance, if the sum includes, for instance, mappings from the sphere to a sphere that have the bracket once with one orientation and once with the other orientation. And so what that looks like topologically is that if you have this space-time sphere, then the worldsheet sort of wraps around it once, but then it sort of folds back at a special point. It sort of folds back and then wraps it again with the opposite orientation. So these types of configurations that have wrappings of both orientations always have these singular points, which are called either zero-size folds or orientation reversed in tubes. So these singular points have to be there, and that these special points in the whole cycle of the worldsheet is mapped to one point. So obviously, that's something quite singular. And so whatever worldsheet we have that describes these mappings has to be able to describe also singular mappings of this type, where again we have these zero size folds. So as far as we could tell, nobody so far managed to write down a completely consistent string theory that really includes all of these mappings. So there were some attempts by Fortmore and Morgula, but they were not very explicit. And then there was an attempt by Petr Hozova to write down what we call the topological rigid string theory, but his attempt was also not completely explicit. I mean, it had some singular terms that were not resolved. So anyway, what we're trying to do, building on these earlier papers, is to write down a string theory that will reproduce this mapping, and essentially it's very similar to the formalism that Hozova constructed back in the 90s, but he built it based on a Navigator-like formalism, while we're using a political-like formalism for the worldsheet that I'll describe that in a moment.
I'm confused about an exponentiation. So the partition function you're writing down.
Yeah, so this is of course the exponential of the connected string worldsheet part. So this, the way that I wrote it here, it's still the original sum that includes both the connected and the disconnected diagrams, but of course it does exponentiate into just the connected worldsheets.
So, but
as usual.
So why can't I interpret and the and tilde as coming from distinct worldsheets?
Well, because it doesn't. I mean, when you take the log of this, then it's still there are still connected things that have both n and until that. Unfortunately, it does not. Yeah, factorize in that way really great, but unfortunately, it doesn't. So there are connected mappings just from the sphere to the sphere that do have both orientations. Yeah, wasn't the case. That's not true. So one point to mention is that in principle, we want to construct the string theory for any value of the Yang-Mills coupling, but the theory simplifies to some extent if we look first at the limit where the Yang-Mills theory becomes free. So already just the free theory, even though we don't have this area term, it still has and we don't have any of these other terms as well. It still has all these complicated numbers that have to be reconstructed from it. So at that limit, we have a completely topological theory in space-time, and that theory is easier to describe. And so we can start by describing that theory and then deforming it to add also this area term. And now the way that, okay, now the clue towards constructing the string theory is something that was noted already in these earlier papers from the 90s, which are that these numbers that appear here can be thought of as the Euler numbers of the space of mappings of this type from a specific worldsheet to a specific spacetime with some specific topology. And what one should consider is the space of extremal area mappings. And so usually when we consider some classical string theory, then its solutions to the equations of motion are just the minimal area mappings. But here it's clear that we shouldn't consider just minimal area mappings because we have these types of mappings with the zero size folds where the area is obviously maximal rather than minimal, because we can always open this fold and decrease the area. So we do have to include also contributions where the area is maximal rather than minimal. I mean, but it is always extremized. I mean, so it is still a solution to the Navigator equations of motion, which extremize the area. So what was shown already in the 90s is that if we look at the space of the extremal area mappings with some specific topology, then these numbers that appear here are just the Euler numbers of the space of all extremal area mappings. So you should just write down some string theory that will compute the Euler number on the space of these extremal area mappings. And that can be done in some version of a topological string theory. And the simplest way to describe it is in some superspace. Yeah, I'm not sure how many details I can give, but so there's a superspace with two fermionic coordinates, and both the space-time coordinates and the metric on the worldsheet are enhanced to superfields in this superspace. And then the action is essentially some superspace version of the Navigator, of the Polytop action. So it's just so these are all superfields in these two fermionic coordinates. more details, you can find them in the paper. So there's one term which is just the Polyakov term, and then if we just have this term, then it turns out that in this, so you can think of this as some topologically twisted theory, which localizes just to the space of the solutions to the equations of motion of this action. So this term localizes to extremal area mappings. Similar way to any other supersymmetric localization. And then one still has an integral over the space of extremal area mappings, and in particular, the reverse zero modes. There are fermionic zero modes also of the sort of the fermionic partners of the coordinates of these extremal area mappings. So to lift these fermionic zero modes, one has to add one extra term, and which we already did, and be chosen to have a form. So it's the extrinsic curvature. So we claim that that with this action, where this is the extrinsic curvature of the mapping from the world sheet to space-time, we claim that that correctly reproduces this expansion. Now the hard part, of course, is to show that it correctly reproduces it. I mean, it's sort of formally it's easy to show that it reproduces it for non-singular mappings, but the problem is to show it for singular mappings. And so there are singular mappings of this type, and there are also singular mappings if you just have, even if you have just a holomorphic mapping from a sphere to a sphere that covers it twice, then that sort of mapping has two branch points, and that mapping also becomes singular when the two branch points collide. So it has to make sure that also singularities of that type are correctly accounted for by this topological string theory. And so we analyze carefully at least some examples of these singularities and of those singular mappings, and we claim that they are correctly taken into account in this path integral, so that this does give us a worldsheet action that correctly describes the partition function of the pure Young-Mills theory. So if people want more details, I can give them later, but since I'm out of time, then let me just describe some of the future directions that we're still working on. So there are many future directions, which are already implicitly mentioned here. So we analyzed so far just this case of the free Young-Mills theory, and of course we'd like to also add this extra Young-Mills term. I mean, so it's sort of obvious how to add the extra Young-Mills term here, and we just try to add the term that looks like the sigma times the bottom component of the square root of this metric. So it's like square root of r, but the problem is that this term breaks the supersymmetry that we have here, so we have to make sure that once we add it, it doesn't destroy all the good properties that we had in the topological theory. So that's what we're currently trying to do. So that's what is coefficient lambda related to the string tension. So that's one thing to do. The other thing that we're working on now is to add boundaries to this worldsheet. So again, now we have a specific worldsheet, so we can add boundary conditions to it. If we add boundaries that have one direct direction, then those correspond to adding Wilson lines, and we should be able to show that the string theory with the appropriate boundary conditions reproduces the Wilson lines of this large Young-Mills theory, which again, there are explicit but very complicated expressions for them that were computed by Gross and Taylor. Well, if we put non-boundary conditions corresponding to dynamical fields, then that should reproduce the Swift model. So again, we're going to have very strong tests of this formalism if we can show that it reproduces correctly the spectrum of the Swift model, but that's we still didn't get there yet. But the hope is that soon we'll be able to quantize this worldsheet theory with appropriate boundaries and see that it reproduces correctly the spectrum of the Swift model. And then we could also try to add massive particles on the worldsheet, which connecting to the previous part of the talk should connect to the adjoint QCD, because at least when we have massive adjoint particles, they should just look like massive particles moving along this worldsheet as in the previous part of the talk. And so the hope is that we can do all these things and therefore get a rigorous way of deriving the string dual of these two-dimensional gauge theories. But of course, we're not quite there yet. At the more speculative level, of course, if we can analyze adjoint QCD for massive particles, we'd like to understand also what happens for small mass when this adjoint QCD becomes strongly coupled, and in particular, when the mass goes all the way to zero, then it even stops confining. So it would be very nice if we could see that from some string theory. Another question we don't know how to answer is there any holographic interpretation of this string theory? So in the way that it's constructed so far, it's just a string moving in two dimensions, and there's no obvious holographic direction, but of course, we certainly expect that once we add dynamical particles, at least, it should be connected to the other types of string theory descriptions that we know where there is a holographic direction emerging. So it would be nice to see how that goes. And then, of course, there's the million-dollar question, which is, can we learn any lessons from this also about gauge theories in other dimensions, but there were in 4 dimensions, but that I don't have anything to say about here. So, thank you.
Question for the speaker?
Neumann boundary condition corresponding to bottom.
So that's corresponds to having dynamical boundaries, which can move anywhere in space-time, and then, of course, okay, so it's natural then to add some mass terms, say, in the boundary, I mean, which would then give the mass, and so that should correspond to a fermionic particle on the boundary, and then depending on exactly which other discrete degrees of freedom we add on the boundary, we should either get scalar quarks or fermionic quarks. So yeah, so it's a model or it's a scalar version. I mean, so that depends on the details of exactly which discrete degrees of freedom we had on the boundary. But it should be possible to get both of them. I mean, just as a different boundary condition for the same closed string theory. So we're trying to get both of these things to work.
Other question? Yeah.
There's a way of getting down to 2 dimensions from 4 dimensions just by taking a flux tube and letting the diameter of the flux tube, the area of the flux tube, go to 0. So you're going from a 4-dimensional theory to a 2-dimensional theory that way.
Well, but in that limit, it still has the transverse fluctuations, right? I mean, this is, I mean, here in the 2 dimensions, we're just living in a 2-dimensional space, and we don't have any transverse fluctuations compared to that space. So that's a different limit. Okay.
Right, there's no question, I think.
What?